Okay, we're back, and we're going to try this again. Point lights, we're going to continue on from the last spot. I apologize for any coughing or things that might come up. I'm kind of getting over being sick, but anyways. Okay, directional lights are great for global lights that illuminate the entire scene. But aside from a directional light, we usually also want several point lights scattered throughout the scene. Makes sense. A point light is a light source with a given position somewhere in a world that illuminates in all directions, where the light rays fade out over distance. Oh, cool. Think of light bulbs and torches as light casters that act as a point light. Okay. Illuminates in all directions, fades out. Okay. In the earlier tutorials, we've been working with simplistic point light all along. We had a light source at a given position that scatters light in all directions from that given light position. However, the light source we defined simulated light rays that never fade out, thus making it look like the light source is extremely strong. In most 3D simulations, we'd like to simulate a light source that only illuminates a certain area close to the light source and not the entire scene. If you'd add the 10 containers to the lighting scene of the previous tutorial, you'd notice that the container all the way in the back is lit with the same intensity as the container in front of the lamp. There is no formula defined that diminishes light over distance. We want the container in the back to only be slightly lit in comparison to the containers close to the light source. Really, let's look at that. Alright, well, it's true. They all appear to be lit the same, I guess. I guess you could say the same. So, alright, moving on. Attenuation. To reduce the intensity of light over the distance a light ray travels is generally called attenuation. One way to reduce the light intensity over a distance is simply to use a linear equation, such an equation would linearly reduce the light intensity over distance, thus making sure that objects at a distance are less bright. However, such a linear function tends to look a bit fake. In the real world, lights are generally quite bright standing close by, but the brightness of a light source diminishes quickly at the start, and the remaining light intensities more slowly diminishes over distance. We are thus in need of a different formula for reducing the light's intensity. Luckily, some smart people already figured this out for us. The following formula divides the light's intensity of a fragment by a calculated attenuation value based on the distance to the light source. Here, I is the intensity of the light at the current fragment, and D represents the distance from the fragment to the light source. Then to calculate the attenuation value, we define 3 configurable terms: a constant term K underscore C, a linear term K underscore L, and a quadratic term K underscore Q. Right. It's a constant because it's not multiplied by anything. This is a linear because it's multiplied by a power of 1. And this is a quadratic because it's multiplied by a power of greater than 1. The constant term is usually kept at 1, which is mainly there to make sure the resulting denominator never gets smaller than 1, since it would otherwise boost the intensity with certain distances, which is not the effect we're looking for. The linear term is multiplied with the distance value that reduces the intensity in a linear fashion. The quadratic term is multiplied with the quadrant of the distance and sets a quadratic decrease of intensity for the light source. The quadratic term will be less significant compared to the linear term when the distance is small, but gets much larger than the linear term as the distance grows. Due to the quadratic term, the light will diminish mostly at a linear fashion until the distance becomes large enough for the quadratic term to surpass the linear term, and then the light intensity will decrease a lot faster. The resulting effect is that the light is quite intense when at a close range, but quickly loses its brightness over distance and eventually loses its brightness at a more slower pace. The following graph shows the effect such an attenuation has over a distance of 100. You can see that the light has the highest intensity when the distance is small, but as soon as the distance grows, its intensity is significantly reduced and slowly reaches 0 at around a distance of 100. Approaches 0 anyways. That is exactly what we want. Okay, choosing the right values. But at what values do we set those 3 terms? Setting the right values depends on many factors: the environment, the distance you want a light to cover, and the type of light. In most cases, it simply is a question of experience and a moderate amount of tweaking. The following table shows some of the values these terms could take to simulate a realistic sort of light source that covers a specific radius distance. The first column specifies the distance a light will cover with the given terms. These values are good starting points for most lights with the courtesy of Ogre 3D's wiki. Distance 7, constant linear quadratic. Oh, weird. As you can see, the constant term k underscore c is kept at 1 in all cases. Distance 7, constant linear quadratic. The linear term is usually quite small to cover large distances, and the quadratic term is even smaller. Try to experiment a bit with these values to see their effect in your implementation. In our environment, a distance of 32 to 100 is generally enough for most lights. Oh darn, I made it 6 minutes in, didn't I? Alright, 6 minutes in and we coughed. Alright. Implementing attenuation. To implement attenuation, we'll be needing 3 extra values in the fragment shader, namely the constant, linear, and quadratic formula terms of the formula. These are best stored in the light struct we defined earlier. Note that we calculate light dir as we did in the previous tutorial and not as in the earlier directional light section. So let's put that in our fragment shader. The fragment shader. Oh, and we're going back to position, I see. Position instead of direction. Let's put the direction in there still, but comment it out. That way it'll still be something I can fondly remember. Constant, linear, quadratic. Okay, good. There we go. Then we set the terms in OpenGL. We want the light to cover a distance of 50. Oh boy. Okay. We might have to stop early, I hear, or something. Okay, GL uniform 1F, light constant, light linear, light quadratic, implementing attenuation. The fragment shaders are simply calculate. Okay. We do need the distance to the light source for the formula to work, though. Remember how we can calculate the length of a vector? We can retrieve the distance term by retrieving the difference vector between the fragment and the light source, and take the resulting vector's length. We can use GLSL's built-in length function for that purpose. Oh, cool. Then we include this attenuation value in the lighting calculations by multiplying. Okay, we're slowly getting through this, but yeah, it's not going well. Alright, so let's see if we can put this in the program, or actually, where are we at? So distance equals length, light position minus position. Attenuation equals 1 divided by all that fun stuff. Okay. Light constant plus light dot linear times distance, which is calculated. Oh, great, I was thinking, how would that happen? Light quadratic times distance times distance. Oh, that's perfect. And that goes in the fragment shader. We could leave the ambient component alone, so ambient lighting is not decreased over distance, but if we were to use more than one light source, all the ambient components will start to stack up. So in that case, we want to attenuate ambient lighting as well. Simply play around with what's best for your environment. If you'd run the application, you get something like this. Okay, my lung has just fallen on the floor, so I'll pick that up and we'll get back to this. Can you believe I went to work today? This is why I want to go into programming. Oh my god. Okay, cube positions, look at all this. Fun stuff. Material, diffuse, specular, light, ambient. Ah, there we go. So now we're getting into the position, view position. Do we have that? Let's look. So probably right in there, I think, is where we're missing the... nope, right down here. Sorry. Okay, so right down there. Yeah, so we're under the stuff under specular. And see, there's that, and then we just need this. These three. Right under specular, right there. Okay, boom. And the fragment. Oh my god. Could I not just have a moment's peace to do this, please? I mean, this is ridiculous. And I have to put the microphone down again. Is there a way to pause the recording? It just stops the recording. There's no way to just continue it. Alright, so let's keep going here. Depends on what. Looks like that's all we need to add. Okay, good. Let's look at the fragment shader. So we do need to add all this stuff here. Ambient, norm, light, diffuse. So let's add the calculation for distance and attenuation. And then the stuff right here. So that's kind of cool. This goes in the very bottom. The fragment shader. Oh my god. My apologies for all the coughing. It's not fun right now. It is not fun right now. So let's just replace that with that. That gives us the attenuation, distance. Perfect. Save that. Okay, let's see it run here. Compile. And run. Nope, something's wrong. Aha, fragment shader, such field and direction. Oh wait, did I commented out? That's right. I didn't. Let's not comment it out then. I probably shouldn't have done that. Whoops. Oh, excuse me. Oh, there we go. So now it's working. Interesting. That's cool. Even though I left the direction in there. Direction light. So actually, is the directional light still working? Huh. Alright, anyways, let's continue on because that looks pretty good. That's good. Then we include the attenuation and we run the application. Looks like that. Okay. You can see that right now only the front containers are lit, with the closest container being the brightest. The containers in the back are not lit at all. Okay. Alright. Okay, so I'm going to stop here and see about some more orange juice. And we made it 13 minutes through 5 pages. We'll see if we can conquer the other 5 pages after this. All right. Wow.